Hello everyone, welcome back. In the last class, we have seen the unit 2, that is transducers. We have seen necessity of transducers, that is necessity of electrical transducers, selection criteria for transducer, active and passive transducers, analog and digital transducers. We also seen strain gauge, the strain gauge working principle, gauge factor, problem related to gauge factor. Then we have seen number of strain gauges, that is bonded resistance strain gauge, unbonded strain gauge, wire type strain gauge, foil type strain gauge. Today in this class we will see the next topic, load cells. So before understanding this load cells, watch this video. Hope you have got some idea about load cells. So what is load cell? Load cell is basically a passive transducer. What do you mean by passive transducer? So it needs auxiliary power to convert one form of energy into another, that is passive transducer. Hence the load cell is a passive transducer or a sensor which converts applied force or a load into electrical signal. So you have seen in a video that some pressure put on that device load cell, so it converts that pressure into electrical signal. The converted electrical signal is proportional to the applied pressure or a force, isn't it? So same the load cell we are going to study here. So these electric signals can be voltage change, current change, or a frequency change depending upon the type of load or a circuit used. The load is same, the pressure or force you apply is the same, but in turn we have one circuit. So depending upon our circuit, it may give the result in a change in a voltage, or in a change in a current, or in a change in a frequency. So in case of a Wheatstone bridge we have seen, so if something changes, the resistance of that circuit will change, isn't it? If there is a change in a resistance, the voltage measured between A and B, isn't the voltage measured between A and B will change there. Instead of a 0 we will get some voltage. So that voltage is proportional to the applied pressure or a force. The same circuit, Wheatstone bridge circuit, we are using in this, but to sense the load or to sense the force we are using this load cell. Fine. So in the load cell, first one we have a strain gauge load cell. Fine. Strain gauge load cell. The strain gauge load cell looks like this. Fine. So this is the side view, this is the top view, this is the actual 3D model of a strain gauge load cell here, isn't it? This is the circuit used. The circuit looks like a Wheatstone bridge, isn't it? This is a Wheatstone bridge. So here strain gauge, whatever you are seeing arm, this arm is connected to these four. Fine, we'll see how this load cell can be constructed. How they are constructed, you can see. So load cell is basically one cylinder isn't it? So with the cylinder, we have some identical strain gauges. The number of strain gauges applied here: 1, 2, 3, and 4. There are 4 strain gauges here. 2 strain gauges R1 and RG are along the cylinder, or this is the R1. Fine, this is this R1, RG is on the other side. This is along the cylinder, and R3 and R2 are circumferentially connected. That means they are connected like this. Fine. Whenever you put a force on the cylinder, the force has to put in this direction. What happens? There is a change in area happens in a strain gauges. We already know how strain gauge will work. Fine. When pressure will be applied on a strain gauge, it expands or compresses. Fine. So depending upon the force, it generates some electrical signals. So same thing, when we apply a force on the cylinder, this strain gauge will get the force, and that will make the circuit to change its stable state. So what happens here? When we don't apply a load here, when no load is applied, what happens? So R1 equals to R2 equals to R3 equals to RG. So the circuit you are seeing here is equivalent circuit for this strain gauge. Fine, this load cell. What happens? This R1, R2, R3 is fixed. This strain gauge RG is connected to all these 4 strain gauges. Fine. If there is a pressure, the pressure will make change this resistance, and this in turn will change the circuit stability. Fine. When there is no force, there is no pressure applied on the load cell. So what is the state? The state is R1 equals to R2 equals to R3 equals to RG. All 4 resistors are same, equal. Hence the voltage measured here in this point is 0. Isn't it? That is the working principle of Wheatstone bridge. When you apply some pressure, there is a change in a resistance happens in a strain gauge. So here RG will change. So RG change makes this circuit unstable, and there is a voltage drop appears at this point. So you can measure this voltage. Fine, this voltage is proportional to applied force. Hence we can measuring the we are able to measure the force applied by measuring the voltage between these two terminals. This is how the strain gauge or load cell works. Fine. Let's see where this load cell can be used. These load cells can be used in road vehicle weighing devices. In a road vehicle weighing devices. So we can measure large trucks, containers. The weight of those vehicles can be measured using this load cell. Next, drawbar and tool force dynamometers, crane load monitoring. So here and all we can use this load cell. Next we have second one, we have a capacitive transducer. Fine. What is capacitance? What is capacitor? So how the capacitor is made? The capacitor is generally a two metal plate device. Fine. Let's consider these lines are metal planes, and these are the connectors. Fine. These are 2 metal plates. In between these plates we have some material. That material may be either a space or air or any other dielectrical material. Fine. What this capacitor does? Capacitor stores energy, isn't it? This you already know. Fine. So now we use these capacitors to measure any change. To measure any change either in a displacement or a pressure, etc. We'll see how this capacitor transducer will work. So capacitive transducer. So this is also a passive transducer. For working, it also needs auxiliary power. So with a variable capacitance. In the last case, in this strain gauge load cell, we had a strain gauge with a variable resistance. Here we use variable capacitance technique. So these are mainly used for measuring displacement, pressure, etc., as I already said. So these capacitor transducer comprised of two parallel metal plates that are separated by a dielectric material. Okay, so we already know the principal working of a capacitor. So how does it work? The operation of capacitor transducer is based on the equation of capacitance of the parallel plate capacitor. We know what is capacitance. Capacitance is equals to epsilon A divided by D. So what is epsilon? Epsilon is a permittivity, isn't it? The permittivity of a dielectric material. The material we use in between the plate is a dielectric material that can, as I said, that can be free space, air, or any other dielectric material. Depending upon our convenient or our requirement, we use a different dielectric material here. Fine. Okay. Next. So as I said, C equal to epsilon naught by A. Epsilon is a permittivity, A is the overlapping area of the plate, and D is the distance between two plates. Let me explain that capacitor. Let's say this is the capacitor which has the two plates here. Fine, it has a dielectric material like this. Okay, so how capacitance can be changed? As we know the formula, epsilon A by D. This area is the area of the plate, D is the distance between two plates. Fine, you can see here. So area means this is the area, this is area. Fine, if area is more, fine, it can hold more charges. The capacitor can hold more charges, isn't it? The formula itself says C equals to epsilon naught A. A is directly proportional to C, right? If A increases, the capacitance increases, isn't it? If area increases, the capacity of a capacitor will increase. That is how the area. This area, if you take a more area plate or a larger plate, we can store more charges, hence more capacity, more capacitance. If you use a less area plate or a smaller plate, it can hold less charge, isn't it? That is the one principle. Another principle is the distance between these two plates. Here you can see the distance between these two plates. That distance is inversely proportional here. The D is inversely proportional. That means if distance between two plates, here the distance between these two plates, if distance between two plates is more, the capacity will decrease, the charge holding capacity will decrease. If the distance between two plates is less, fine, the charge holding capacity is more, hence the capacitance is more. Hence if distance is less, the more capacity. If the distance is high, the less capacity of a capacitor, that is less capacitance. You can see this formula itself says the principle of a capacitor. If the area of plate is more, the capacitance is more. The distance between two plates is more, the capacitance is less. Also, it also directly proportional to the epsilon. The material we use as a dielectric, if its permittivity is more, the capacitance is more. If the permittivity is less, the capacitance is less. That permittivity, that is that dielectric constant, so that permittivity can be given as epsilon naught into epsilon r. So epsilon naught is a permittivity of a free space, and epsilon r is a relative permittivity. Let's see how we can use this capacitance principle to measure pressure or displacement. Fine, we have three cases. What is that three cases? Capacitive transducer using change in area of plates. Second one, capacitive transducers using change in distance of the plate. This is area of the plate, distance of the plate, distance between the plates, and capacitance transducer is using change in dielectric medium. As we know, the capacitance is proportional to what? The area of plate, distance between the plate, and the material used between the plates. Fine. So if you put a pressure, fine, if you put a pressure here, if you put the pressure on this plate, what happens? The plate move towards another plate. That means the distance is decreasing. The pressure makes this plate to move towards another plate, and distance is decreasing. If the distance decreases, the capacitance increases. Hence we are making, or we are converting that pressure into a capacitance change, or a change in a capacitance. That can be done in a second case. In the third case, by pushing this dielectric material inside, we are inserting more dielectric or different dielectric between the plates. Hence the epsilon will change, because epsilon is nothing but epsilon naught into epsilon r, isn't it? So if you put a extra material, or if you take out the extra material by putting a pressure, the change in a dielectric material happens. So this in turn will make change in the capacitance. So hence this capacitor can be used, this type of sensor can be used as a transducer. By putting a pressure, we can make change the area, we can make change in the distance between plate, or we can insert or take out the dielectric material. So this will make change in a capacitance. Hence the pressure is converted into change in a capacitance. That change in a capacitance can be measured, and we can measure the actual force applied or a pressure applied here. We will see features of capacitive transducer. First one, accuracy. Definitely it has a high accuracy, about plus or minus 0.2% of a full scale. It has got a minimal mechanical motion. A small change can be easily measured. Range capabilities, long-term stability, it provides long-term stability, high level output, and electromagnetic compatibility we can expect from this capacitive transducer. Also is a resistance to harsh environment. It can work under a harsh environment. What is the advantages of capacitive transducer? It requires extremely small force for operation. As minimum or a small force can be measured easily here. It requires small power for operation. Since the capacitive transducer is very small, it obviously requires small power for operation. Frequency response is good. A resolution of the order of 2.5 into 10 to the power of 3 we can expect from a capacitive transducer. So it gives higher input impedance, therefore loading effect can be minimized. Fine. What is the disadvantages of capacitive transducer? So it is very much sensitive to temperature variations, the possibility of erratic or distortion signal due to long lead length. Fine. If you use long leads, then it may give some errors. They show non-linear behavior on account of edge effect. This can be eliminated using a guard rings. So we have a special material called guard rings to avoid this edge effect. Where this capacitive transducer can be used? It can be used as frequency modulators in RF oscillator, in capacitance microphone, to use the capacitive transducer in an AC bridge circuit, to measure force and pressure, and to measure humidity in gases. We can use this capacitive transducer. So there are many applications, not only 5. This is not limited to 5. We have many applications where we can use this capacitive transducer.
Capacitive transducer. The capacitive transducer can measure static and dynamic changes. Let us see a capacitor microphone. In a capacitor microphone, sound pressure varies the capacitance between the fixed plate and a movable diaphragm. The capacitance of a parallel plate capacitor is given by this equation. The capacitance is directly proportional to the area of the plate, and inversely proportional to the distance between the parallel plates. Any variation in the area, or in the distance between the parallel plates, will create corresponding variations in the capacitance. When a force is applied to a diaphragm, which acts as one plate of a capacitor, the distance between the diaphragm and the static plate is changed. The resulting change in capacitance can be measured with an AC bridge.
So next we have topic Hall effect transducer. So let's understand what is Hall effect. Watch this video and come back.
Hello, Dan Nelowski here from howtomechatronics.com. In this video, we will learn what is Hall effect and how Hall effect sensors work. The Hall effect is the most common method of measuring magnetic field, and the Hall effect sensors are very popular and have many contemporary applications. For example, they can be found in vehicles as wheel speed sensors, as well as crankshaft or camshaft position sensors. Also, they are often used as switches, MEMS compasses, proximity sensors, and so on. Now we will go through some of these sensors and see how they work, but first let's explain what is the Hall effect. Here's the experiment that explains the Hall effect. If we have a thin conductive plate as illustrated and we set current to flow through it, the charge carriers would flow in a straight line from one to the other side of the plate. Now, if we bring some magnetic field near the plate, we would disturb the straight flow of the charge carriers due to a force called Lorentz force. In such a case, the electrons would deflect to one side of the plate and the positive poles to the other side of the plate. This means if we put a meter now between these two sides, we will get some voltage which can be measured. So, the effect of getting a measurable voltage, as we explained above, is called the Hall effect, after Edwin Hall, who discovered it in 1879. The basic Hall element of the Hall effect magnetic sensors mostly provides very small voltage of only few microvolts per Gauss, so therefore
Hope you understood that Hall effect principle. Let's consider again. Let's see again. So this is the metal and current is applied in this direction. The current is in this direction and the magnetic field is applied in this direction, which is perpendicular to a flow of a current. So this is the perpendicular to flow of current. Fine. If we apply magnetic field to this conductor, what happens? The charge carriers will drift towards one side of the plate and there is a potential difference developed between these ends. Let me change the color. At this end and at this end there is a potential difference developed due to applied magnetic field, because this is the conductor. So current flowing in this direction, when we put a magnetic field perpendicular to the flow of a current, there is a potential difference at the end of the plate. So this is the principal working of a Hall effect. Fine. And this plate is a semiconductor plate and this element is called a Hall element. You can see here, this is called Hall element. So the thin sheet of semiconductor bar is the Hall element. So blue color plate, whatever I said, that is the thin semiconductor plate, that also known as a Hall element. Okay, and the voltage produced here at the edges of this Hall element is in terms of the microvolts. Fine. So you can see here they have given the voltage is known as Hall voltage and it is typically in the order of few microvolts. The voltage developed here or potential difference developed here, that voltage is called a Hall effect and it is in terms of or it is in order of a few microvolts. And the voltage developed here at these terminals is dependent upon four factors. What are those four factors? Dependent upon kh. Okay, kh is constant. It is only dependent upon a three variables b, I and t. The kh is a constant. That constant is nothing but we call it as a Hall coefficient. Fine. And we can say, so the voltage, Hall voltage is equals to kh into b into I divided by t. So what is VH here? VH is the Hall voltage developed at the edge of the thin semiconductor bar. KH is a Hall coefficient. B, the magnetic field strength applied. I, current carrying by the semiconductor bar. And T, thickness of the specimen along the magnetic field. Thickness of the thin semiconductor bar is nothing but here T. Fine. So voltage developed across the edges is depending upon these three factors B, I and T. Next, the Hall effect may be used to find whether the semiconductor is N type or P type. Though this is the application of a Hall effect. So why do we how do we use, or where do we use this Hall effect? So to find the semiconductor whether it is a N type or a P type, for this we can use this Hall effect. And to determine charge carrier concentration, the concentration of a carrier charges can be determined by using this Hall effect. Fine. Till now we have seen what is Hall effect and principle of Hall effect. We will see some applications where we can use this Hall effect. We can use this Hall effect for a transducer. Okay, so these are the Hall effect transducer are the transducers in which Hall effect is used to measure various electrical and non-electrical quantities. Clear? So we will see number of applications. First one will say Hall effect displacement transducer. Okay? In the diagram you can see Hall effect displacement transducers. So this is a setup for Hall effect displacement transducer. So what happens here? The Hall effect element is located in the gap adjacent to the permanent magnet, and the field strength produced in the gap. Due to the permanent magnet, it is changed by changing the position of the ferromagnetic plate. The voltage output of the Hall effect element is proportional to the field strength of the gap, which is a function of the position of the ferromagnetic plate with respect to structure. Thus, displacement can be measured by the Hall effect transducer. Very small displacement up to around 0.025 mm can be measured by this method. So here the Hall effect element is placed here. So this is the Hall effect element, and permanent magnets are placed here. So this is the ferromagnetic plate. So this plate will move towards this, and 2 and 4th, like this plate will be moved in this direction as well as in this direction. Fine. So depending upon the position of the plate or a displacement of the plate, the the Hall effect element will produce the voltage, Hall voltage. So if the plate comes near to it, the more voltage will produce. The plate go far from this place and less voltage will be produced. By this we can measure the displacement of the plate. And the next application is fluid level measurement. Fine. The fluid level measurement, the fluid level measurement uses the Hall effect principle only. So we can use this fuel level measurement in a automobile fuel indicator. So what happens? Let's consider this is a tank. Fine. This is a tank, and there is a magnet attached on a floating material. This is the floating material. The magnet is attached at top of the floating material, and this floating material is set up with this springs. There are number of springs attached. So whenever we put a fuel, this floating material will float and move towards this top. Fine. So there is a Hall sensor placed here. Whenever this magnet move towards the Hall sensor. The Hall sensor will produce more voltage, indicating it is the fuel is more. Fine. If the fuel is more, this magnet will be nearer to this Hall sensor. If fuel becomes less, or when tank becoming empty, it move downwards. Hence, the distance between this magnet and the Hall sensor will increase, thereby indicating that there is a low fuel. Fine. So this setup uses the Hall effect principle again. So this can be used. Fine. I'll just read out this. A fuel level indication can be obtained with the Hall effect sensor by attaching a magnet to float assembly. So this is the float assembly here. As the float moves up and down with the fuel level, the gap between the magnet and the Hall element will change. The gap changes the Hall effect and thus the output voltage. This gap creates a Hall voltage, and that Hall voltage indicates whether Hall voltage indicates the level of the fuel. This is as simple as this. We'll stop this lecture here. We'll continue in next class. Thank you.